And good morning also from us, and welcome to the Arctic Climate Session. And we will start almost directly. We have 8 presentations with 10 minutes each and some time for questions afterwards. And we have a very wide spectrum of presentations, representing nicely also the variety of the research at Bolin Center. And with this, we start with the first talk, which is by Qiong Zhang about Arctic warming in EC-Earth Pliocene simulations.
Yes.
Thank you.
Thank you. Yeah. I guess you already staring this title for a while, and you are wondering why your co-author's name is so similar. So that's very, yeah. Yes, you could see it's very confusing, but yeah, we have to live with that. Yeah. Okay. Yeah. And so today I will talk about this Pliocene warming because when we now experience this very, very high CO2 concentration, we know that last year we already passed 400 ppm with this level. And we know that actually now it's very high. In glacier interglacial cycle, usually it's never, above this pre-industrial level, but now we are very high. And the nearest warm period in the Earth's history actually happens. This happened before, but it's very earlier. Around during the Pliocene that it's 5.3 to 2.55 million years ago. So we had the same high CO2 concentration. So this is from the marine records. You could see that during this period, the CO2 level also reached 400 ppm and even sometimes even beyond that concentration. So our motivation that we join this PliMeep and try to simulate the climate at that time and see what happens. So during Pliocene, not only changes in the CO2 level, there's also something different from today. For example, that there's some change in these inter-ocean gateways. For example, that Indonesia through this one open and then Bering Strait is closed and the Panama Seaway is open. So this is something different from today. And another difference is also in this ice sheet distribution is also different from today. As during Pliocene, this ice sheet in Greenland become very small, only a small part left there, and Antarctic ice sheet also decreased quite a lot. So, and then in the scientific community, there's a few 3 crucial features for the Pliocene warming. We know that Pliocene warming is 2 or 3 degrees warming than today, and then major features for this warming is, first is people know this is in the high latitude there's strong polar amplification. Then another one in the tropics, they found that there's lower western-eastern SSE gradient. That means it maintains a permanent El Nino state. And then another one, it also shows that Zeno and Meridional SST gradient is also weak. That will affect the hydraulic cycle. So this is different because we know that from the IPCC report in the future, for the future scenario, we get this wet get wetter and dry get dry. But in the Pliocene, it seems that wet get dry and dry get wet. So this is difference from today. And then we did this simulation with EC-Earth model. And EC-Earth is the Earth system model we used here in doing a lot of the paleoclimate simulations. And then we get all the boundary conditions or protocols from PliMeep, and the PRISM is a geological community that get all this paleoclimate proxy data in the past. And so for set up this simulation, we follow this Pliocene for Pliocene because we exactly want to do what happened in Pliocene. That's why we also change, not only change the CO2 level, but we also changed the land sea mask, topograph, barometric in the ocean, and ice sheet, and also the vegetation. And our model resolution is a low resolution T159, it's about 100 kilometers. So for this simulation, we did about 500 simulation, and when we see the climate change, we refer to the pre-industrial state. So for the major results, we want to answer that if we see this strong Arctic amplification, then we say yes, we saw this very strong Arctic amplification, and if we calculate the ratio, it's about 3.5. And do we see the permanent El Nino-like condition? No, we didn't see this, but we see that if we do the statistics, we see that we have more El Nino and less La Nina event. But today I will focus on this Arctic amplification part. So this is the general circulation for this general pattern features for this long simulation. You could see this is 500 years. And usually when we do this kind of simulations, this is called equilibrium simulation. So we need to wait until the model reaches equilibrium. So when you see this trend, then this is the spin up time. So usually when we do the analysis, we don't consider this part, but we only take the rest part for our analysis. So this shows global mean SST. Then we see this is 1.85 degree warmer than PI. And then we also show the ocean character from this AMOC. We found this AMOC is 2 swirl weaker than PI. And this one actually is not very consistent among the models. Some models show stronger AMOC, some models show the weaker AMOC, but in our model it shows weaker. And if we look at these patterns in SST, this is our annual mean that SST in the EC-Earth is the change, this Pliocene minus pre-industrial. You could see that very strong Arctic warming shows in our model, and there's also warming in the South Hemisphere. And this is the prism reconstructions. Even for the Arctic region or North Atlantic, there's only a few points, but it shows very strong warming in the prox data, and it's our result consistent with this. And this is a result from 2012, this multi-model mean, because some other group already did this simulation before, and then we saw that actually in the other models, they didn't show this very strong Arctic warming. So that's why when I present our results in Pliocene workshop, that people said, okay, you need to explain why we didn't get this strong warming and your model gets this strong warming. That's why we need to look at the mechanism, what caused this very strong warming. So here I show this. This is the annual mean that SST. We see that this strong warming shows both in the SST and surface air temperature. And in the surface air temperature, it's much stronger. Usually when we talk about Arctic amplification, usually we calculate from the surface air temperature. But this is the annual mean. But if we look at the seasonal cycle, you could see actually there's different behavior in this SST and SAT. In SST, much warmer in summer season, and then you also can understand that's why, because melting of the sea ice. And actually, but in the air temperature, actually most warming is not in summer, but in winter. And we further will explain why it's warming in winter. So we use this climate feedback and response analysis method. This method a little bit complicated, but this is a very good method that it's kind of use do this audation that if you know that there's temperature change, this method can tell you which process, which forcing, which feedback contribute how much percent. It can quantify the contribution to this temperature change. I won't go through this method in detail, but if you are interested in this, Matcha Coleman have the poster that describe this method very in detail. You could go to her poster. So from this feedback, I just show these results that we see that actually albedo feedback in summer, you could see mostly in summer, contributed much more due to the sea ice decrease. This is the sea ice and albedo, this feedback's relationship, and it contributes 84%. And then in winter, we found actually, we also calculated the water vapor feedback, cloud feedback, all the feedbacks, but it turned out this turbulent feedback in winter is sensible heating, and the latent heating contributed to a lot. It's also related to sea ice decrease. So it's contributed separately like 59, 74%. So you could see that we can quantify how much percentage contributed by the different physical process. So now I come to this summary. So our simulated Pliocene warming pattern is well agreed with prism reconstructions, and we also can explain why that. Actually, this very strong Arctic amplification is due to the significantly reduced sea ice. And then dominant this albedo feedback is 84% responsible for the summer warming, and then this strong turbulent heat flux responsible for this winter warming. And if you are interested, this paper is now in Climate Plus, you can read that. And I also would like to say that, okay, now we learn something that from the past, and what does the future tell, that because now we see that when in Pliocene, when we have 400 ppm CO2 concentration, we see this ice decrease very much. I didn't show that, but we really got some ice-free summer in Arctic, and you also see that Greenland ice sheet almost gone. So this might happen in near future when we have this increased CO2 level now, year by year. So, yeah.
Questions for Qiong?
The strong turbulent heat flux, that can't in itself be a cause. That's just a diagnostic of what's going on. That's a response to other things that are going on in the Arctic. And so I still think you haven't identified what the actual cause is of the winter warming in this model. Something else, top of atmosphere, cloud effects, differences in your sea ice model, or what is driving that turbulent heat flux. So I was wondering if you know the reason that the turbulent heat flux is increasing.
Yes, because we calculate from the long wave radiation and short wave radiation, turbulence heat flux is mostly due to the long wave radiation. Of course, that maybe comes from the water vapor and the cloud. But with this method, we can identify this is the most largest part. You are right. That is also the reason. Yeah.
Another quick question? So the other models that didn't show this strong amplification, they have much less sea ice decrease?
Yes, there's one paper in 2013 shows they didn't, their sea ice in decrease is much less. Yeah.
And do you know why?
I think that in EC-Earth, in our model, sea ice is much sensitive to all these four things. This we also see the turbulence that for ICP 8.5 analysis.
When I have the microphone, can I also take the opportunity? Thanks, Qiong. You showed in one of the figures some temperature anomalies, and it indicated cooler temperatures over Europe, for instance, and also in parts of North America and in Asia, I think. Did you look into the reason for why these areas were cooler?
You mean over the land?
Over the land, exactly.
Oh, we didn't look at that in detail, yeah.
You didn't, or?
Oh, we didn't, yeah, because we focus on Arctic. But yes, there's a small part of it, but we didn't think about that reason. But that might be also similar for today's, because today we also find a small cooling over the Eurasia continent. It might be the same reason, but we didn't look at the mechanism for that part.
Okay, but that would be interesting to do.
Yeah.
Hi, in your data model comparison, the data seem to suggest very small changes in the southern ocean, the southern hemisphere, but your model shows warming. I was wondering what the uncertainty is, though, on those data, and whether your model is in line with what the data say once you consider the uncertainties.
Yes, for the southern part, actually, data, if we go back, there's not too much data in the southern part. It's only very few. And then there's also argument that there are large uncertainties there. That's why this PRISM now, they released a new data set. Actually, we had the workshop 2 weeks ago. And the new data set for the southern hemisphere part, actually, is very different from the first set. So that means that, yeah. So I think that in the data community, they also a lot of very large uncertainties, especially so far back in the past.
Okay, we have to end there and go on to our next speaker.
Yeah,
Let's thank Qiong again and welcome Pasha Karami, our next speaker.
Hey, good morning, everyone. So I'm very glad to give this presentation today in Bolin Center. I will be talking about Arctic sea ice variability, and thanks to the previous speaker, so some stuff became easier to go through my slides. So I will be talking about Arctic sea ice variability and the causes behind. So to start, I show two figures on the right. So from satellite images, they are related to the two different years, so 1980 and 2012. And what we see here, these colors are showing where it is covered by sea ice. And when it becomes dark blue, that means that there is no sea ice. And as you see from 1980 to 2012, it's about more than 3 million square kilometer was disappeared from the sea ice. And I will be talking about this. So just since I have these figures there, well, in this presentation I will address sea ice area, which means all the area average on these colored regions. So sea ice area I show here on the left, and then versus time, going back to 1900, and I show two different data sets for ERA20C and NCEP. They are both reanalysis, and as you see, the sea ice area declines somewhere from mid-20th century and until start of, say, until 2010 that we have these data. There are some weird, you see here, some weird curves there, and that's in 40s, some missing data. And I corrected those, and I applied a method which called empirical mode decomposition to get the long-term mean, so what you see there as dashed for both data sets, and to basically remove these dashed lines to get to the anomalies, because I'm interested in the variability. So what you see here, again, the two data sets and the anomalies, and the color shades are related to whatever is above or below standard deviation. And I also show the correlation between two data sets, which is quite high. So you see already here that there are some interannual and interdecadal variability in the sea ice area. And also if you look at the spectral analysis, so there is something, can we get rid of this one? Or so, yeah. So there are some like 2 to 5 years, around 15, oops. So all the sea ice disappear. Okay, 2 to 5 years, say like around 15 to 18, and around 30 years. So these are the significant, and it says that sea ice variability had such interannual to interdecadal variabilities. Going back to, say, the time series I showed there. Now, if you want to check, for example, how much sea ice loss happened, for example, during 1998 to 2010. I can tell later why I chose this period. So the total sea ice loss was something about 2.8 million kilometers square. And then the dashed part is what I call the long-term mean. And the share from that one is like around 1.6. This is the part that I say that is most probably linked to the anthropogenic warming. And it goes well with the global warming of the temperature. And also IPCC report, I can cite that with many other studies. So this dashed line, we can link most probably to the anthropogenic warming. So that's the share from there. But the rest is related to the interdecadal or interannual variability. So if you look at, if we divide our anomalies and then to do two modes, so they like the interdecadal and interannual, and then I show this share from interdecadal mode here and then interannual mode. So basically that's interdecadal mode is like something 30%, 33% of this sea ice loss in that specific period. So what can cause sea ice change? So different factors, I put some here. So for example, changes in the ocean heat transport from Pacific side, we get heat from Pacific Ocean, and also from the Atlantic, we get heat to the Arctic, and also atmosphere, again, heat transport from both sides. And also in the upper levels, as discussed in this paper, from the upper atmosphere, you can also warm up the Arctic and reduce sea ice. And these two papers, for example, summarize some stories there, which I will not go to the details of those. You can check them. And now to start with the cause of interdecadal variability. So I start with making composite maps, just and what it means. So if we make the interdecadal mode of the sea ice, so what you see here, the black one, so whatever is above standard deviation, I call high sea ice, and below that I call low sea ice events. And all the averages, we take the average for the high sea ice and then minus low sea ice, and then that makes the composites. So I also compare that with the surface air temperature in the Arctic. So this, say, pink and purple show how the temperature was, and there was a moderate negative correlation between temperature and sea ice on interdecadal mode. So going back to the composite story, so that's the composite for the sea ice. So basically all the years with high sea ice minus low sea ice, this map tells us where the sea ice is the most affected by the interdecadal sea ice variability. So you see all those regions that would be the most affected. Now, I said like ocean and atmosphere are providing heat, or they bring heat to the Arctic. So it's fair to look at them first. So like SST is a good candidate. So that means sea surface temperature, and SLP here, sea level pressure. So if you look at the composite maps for the SST, you see that there is some cooling there around the Arctic, which goes well. This is about high sea ice minus cold, so we expect colder temperature there. And I will discuss this in the next slide in more details, the story about SST. Talking about the sea level pressure, so we see a dipole-like pattern here. And this is the well-known famous Arctic dipole that people address in many studies regarding Arctic sea ice changes. In this specific case, that we have low pressure on the, say, more in this over the central Arctic, then we get less export of sea ice, and therefore less sea ice, more sea ice in the Arctic. And the opposite phase would be more export and less sea ice. So, and this is how this phase is affecting the sea ice. Now, as I promised, so the story about the SST. So then there are two very important modes of interdecadal climate variability. And then one is called Pacific Decadal Oscillation, and one is called Atlantic Multidecadal Oscillation, so PDO, and then AMO. And these two are the most important ones, which are driven by the ocean, like originated from the changes in the SST in the ocean. So I put the EOF of SST, and on this plot you see this is the PDO, and that on the right, that's the second EOF, and that's the AMO phase. Or AMO mode, and the left says that how the time series and how they evolve in time. So basically how to link our EOF to the PC1 and PC2 of the EOFs. So how to interpret this SST here? So it's not entirely similar to this, but when we get the help from the time series. So I just highlighted for example, the events that we see here for the high sea ice or low sea ice. And in AMO, we see especially like before, this is a cold phase of AMO, and then after that we get high sea ice. This is a warm phase, so it's just switch it. And this is a warm phase of AMO, and then you get less sea ice, and so on. So AMO shows actually good correlation, and like with the lag correlation of say about 5 to 9 years, and it leads the sea ice events very well. I still need to find out what PDO does here, but that one also is important in terms of interaction with AMO. So now reaching my conclusion, and I'm over by time. So in the first part, I showed the contribution, like something was between 1996 and 2010. The internal climate variability could have like 35% contribution to the sea ice loss. And another message is that AMO is leading sea ice variability, say by 5 to 9 years. So that's it. Thanks a lot. There was time for questions.
I wonder a little bit how you dealt with the uncertainty, because your data there from 1979 and onwards, you have satellite data, and before that you do not have satellite data. Have you been able to, have you incorporated the change of uncertainty of your data sets in terms of sea ice distribution and temperature as well?
Not for each specific year, but for this, for example, for the difference between 1996 and 1980, I would say the difference was really little, so even less than 10%. So that value I basically showed, but I don't know, 2 point something, that was maybe for the satellite data was 2.7, something like this. So it was very not, in terms of percentage, was not very large, yeah.
Are there more questions?
Sorry, I came from the other room. Okay. Okay. I was in the other room and the slide didn't work there, so I missed the start. So which data did you use? I missed it. I'm sorry.
For
this study. Where did the data?
Sorry, which data?
Yeah.
Oh, okay, yeah, the ERA20C and NCEP. Yeah.
So they were not a coupled system, or were they?
Well, ERA20C is it's driven by, so it's a reanalysis, so it's driven by observations and models and also assimilation. So.
So in this reanalysis, the ocean and the atmosphere, are they coupled system?
Well, I think what they do, they take the SST from the observations and all the station things, and then they run because it's a atmosphere model and force with the SST from observations.
Okay, thank you. That's what I want to know.
Yeah.
Thank you. One more question there.
Why did you use the years of 1980 to 1996?
The reason was that because that's a period basically when you want to look at the internal variability, because they have a period. So if you take the start of a variability and the end, which is belonging to one period, then you end up with 0. So it doesn't show any variability related to that specific thing. So that in that specific year, so 1996 was almost close to the peak of the interdecadal variability, and 2010 is the minimum of that. So then you need to basically look at that. Because if I take, for example, 1980 and 2000, then I would end up 0 for the interdecadal variability because it's a periodic cycle. Yeah.
Thanks a lot. So I think we will move on to the next speaker, and that is Sara Broomé.
All right. Hello. So I am Sara, and I want to talk to you today about the North Atlantic Arctic Ocean connection observed with satellite altimetry. And so what I mean with the North Atlantic Arctic Ocean connection are the Nordic seas, which you can see here in the red box. So these seas are here between Greenland and Scandinavia, and they are transporting heat into the Arctic from the North Atlantic. So this is going to be talking physical oceanography. And from Arctic oceanography, my experience is that the Nordic seas are not included in the Arctic. They are also usually not included when you talk about the North Atlantic. So I think they are sort of an in-between ocean area, sometimes maybe a bit forgotten or overlooked or taken for granted by both of these communities. So my main message here today is that a lot of interesting things are happening in these oceans, and I hope I will prove that to you. So as I said, they are transporting heat into the Arctic from the North Atlantic, and you can see that by this warm tongue in the sea surface temperature, and also there is cold water transported out from the Arctic into the North Atlantic, and also ice is transported out, and so on. So if I can only tell you one thing about the Nordic seas, it would be about the bottom topography. So the current systems in these oceans are constrained by bottom topography, by conservation of potential vorticity. But also there's a ridge here between Greenland and Scotland. So water from the North Atlantic has to travel over this ridge. And also waters that are formed in the Nordic seas, dense cold water, have to flow through the sills in this ridge as overflows. So this is very important for this region, and it's very much topography constrained. So this is a schematic of the northward ocean currents, which I'm going to concentrate on most in this talk. So they come from the North Atlantic, they follow the continental shelf northward in two current branches. And if you were to take a section across these basins of temperature, it would look something like this. So you can see that the warm Atlantic water is constrained here to the upper few hundred meters, and they only reach halfway into the basin. And this is also because of topography. So they are actually constrained here by this topographic ridge running through the basins here. Okay, so what I use to study these, as it also said in the title, are satellite altimetry, or specifically absolute dynamic topography. So the gradient in this sea surface height is proportional to the current speed. It includes both a steric signal from the ocean column's temperature and salinity, but also a bottom pressure signal. And the data are available from January 1993 up to May 2018. It's on daily fields, quarter degree Cartesian grid, and in this talk it's going to be in monthly means all the time. So some very short scale variability is not here. So I'm going to tell you a few short highlights from my research on this. So we start with the slow propagation. There are many who have seen that or tracked propagation from the North Atlantic into the Arctic, and they see that it's slow compared to the current speed. And this you can also see in this satellite altimetry. So this is a cross-correlation analysis along the current, so along this black line, which is the 700-meter depth contour. And if we correlate all points downstream with this x base point, you will get this. So this is cross-correlation. You have lag in months here, and on this axis you go further downstream towards the Arctic. So there's an instantaneous high correlation, but there's also some pattern you might be able to see that is an elevated correlation that runs here with increasing lag and distance. So you could compare this to this simpler figure maybe, which is just correlation between two current meters, one about where I have my base point and one further north. And you can see that the velocity, the black line, has an instantaneous correlation. That also is the correlation that is instantaneous in the sea surface height, which is basically the atmosphere directly affecting the large scale area. But then you can see that the correlation in temperature has its maximum at a lagged time. So that is this lagged correlation on this side. So the mean current speed would be 15 centimeters per second, but transport of heat anomalies is actually much slower at about 2 centimeters per second. If you were to look at the linear trend and the sea surface height, you can see that it's mostly concentrated, the positive trend, in this area. And you can also see that it has a very intricate pattern. You can compare it to the linear trend in heat content. So they have some similarities in their pattern, but also some things that are different. So you can see that this is maybe more structured than the heat content. And you can ask why this intrinsic pattern. So if it were just heat coming in from the North Atlantic and it would get hotter, you would sort of assume that it would distribute evenly throughout this Atlantic water layer, but it obviously doesn't. So you can ask why this intrinsic pattern. And I'm just going to quickly tell you that it could be ocean-atmosphere interaction, it could be wind, something like that, but it turns out that it's ocean transport within this system that's the main culprit. And this satellite altimetry time series is also long enough now so you can start looking at some decadal variability. So if you divide this trend into 2 periods, you can actually see that most of the positive trend is in the first period, between 93 and 2002 in this case. And if you, so you can see that most of the difference between these 2 maps is in this specific area. So this shaded area, I now take the sea surface height and I average over this area and make a time series. So the blue here is then the sea surface height, or the ADT. The black line here is the globally averaged ADT. So the trend in this globally averaged ADT has been removed from my ADT data to look at regional dynamics. And you can see in this straight line there's a small positive trend remaining. But if you divide it up into these 2 periods, you're going to see that most of the trend is actually in the first period, and there's actually a slight negative trend in the second period. And you can, of course, choose different periods, but I think by eye can see that it's quite different, the 2 periods. And again, you could ask yourself, what is causing this difference or in the decadal variability? And again, it's going to be ocean transport rather than atmosphere interaction. So my take-home message is that the Nordic Seas is everything but a passive intermediary between the North Atlantic and the Arctic Ocean. And I've also pointed that there's a slow propagation compared to current speed, and that ocean transport is more important than the atmosphere interaction. With that, I thank you.
Hello, everyone. My name is Ramon Fuentes, and I will present some research that we are doing in SMHI. I have done this work together with Torben, that is here. Yeah, I will speak about Arctic freshwater exports in coupled global models. So, well, I wanted to make an introduction, but I think, well, the presentation by Sara and Pasha, they were really helping. Anyway, I will speak about a little bit about the mean climate, or the mean circulation over the Arctic. In general, the ice is really influenced by the atmospheric circulation. This is the mean atmospheric circulation over the Arctic, and we can see that we have a anticyclonic gyre here over the Beaufort Sea. And this is where you have the highest amount of ice and fresh water as a volume. And you can see that there's the transpolar drift helping to export the ice from the Arctic towards the Atlantic. In this case, the Bering Strait serves like an import, is an import gate towards the Arctic, and the Davis Strait is also collaborating with some exports. But if you see the numbers, the Fram Strait actually has the biggest ice and liquid exports from the Arctic towards the Atlantic. So I will focus mostly on the Fram Strait. The Barents Sea opening has actually a kind of balance. It's just zero more or less. So it doesn't contribute so much towards the freshwater export towards the Atlantic. That's why I will focus on Fram Strait. So once the freshwater, liquid, and ice has crossed the Fram Strait, it goes all the way down across along the Greenland coast with the East Greenland current towards the south. It reaches the Labrador Sea, and when in some campaigns it has been measured the temperature and the salinity um, over this region, and you can see that actually, if you measure, you see that there's a high correlation of temperature and salinity. When you have a lot of ice export that it will be melting along the coast, it will reach this area and it will be creating a cooling effect over this region. And also you will have, since it's carrying fresh water, the salinity will drop. And this is another point in the same area. So temperature and salinity are really quite highly correlated, and this is how the great salinity anomalies are following the subpolar gyre. So it starts when measuring from here, you can see that from 89 to 90, it will be back towards the Fram Strait in 7 or 8 years later. So it's quite a slow circulation there. How is this reproduced by models? Well, this is shown how a coupled GCM reproduce this effect. So you can see that 1 year after the export of ice and across the Fram Strait, you will see a decrease in of salinity in the southern part of Greenland. You will see a reduction in temperature, and you will start to have high pressure. After 2 years, you will have the anomaly salinity a bit farther to the south. You will have this as well, the temperature that is correlated with the salinity anomaly, and then you will have you start to develop like a kind of a positive phase of the NAO, having a higher pressure over the southern world, over the Atlantic, and a bit of a lower pressure over Greenland and Iceland. But how do CMIP5 models reproduce this? Well, we are contributing with a Primavera project. In this project, we are seeing what's the impact of increasing resolution and of using different forcings in the atmosphere to the same processes. So you use the same configuration in the models and you just change the resolution. So I'm showing here, for example, when you change the ocean resolution, you have in the freshwater content, when you compare with observations, with the reanalysis, you can see that the models, they don't do so bad. They reproduce the patterns with some anomaly, with some anomalies, of course. You have more a lack of fresh water in high resolution, high ocean resolution, and when you increase the atmospheric resolution, you also have an impact. So the impact, when I subtract the coarse resolution minus the high resolution, you can see that the coarse resolution shows much more fresh water over the Arctic. And when we compare the change in atmospheric resolution, you see that the coarser the resolution, you have an accumulation of fresh water towards the Laptev Sea and less fresh water over the Beaufort Sea. And this change is systematic. Now, regarding the ice content, we can see also a systematic change. When we compare with observations, models tend to reproduce, they have more uncertainty when we compare with freshwater volume. But these are pre-industrial simulations, so we expect already to have more ice than in observations. In this case, they are present-day simulations. So this could be more or less comparable with this, but you can see that there is more uncertainty. By subtracting the core resolution minus the high resolution, you can see that there is also more ice in the core resolution, and you have more ice also in the coarse atmospheric resolution compared to the high atmospheric resolution. But how much water, liquid, fresh water, and solid and liquid is passing through the Fram Strait? Well, we calculated for all models. I'm showing just the atmospheric simulations here. These are in blue is with the blue rectangle is the fresh water, and liquid, and this is the solid. So liquid is up and solid is here. So you can see that there is a really strong decrease of ice transport as you increase atmospheric resolution. And there is a not so clear effect, but you in the mean you have much more freshwater export across the Fram Strait when you have higher resolution. This will afterwards impact on the convection. When you have an increased freshwater transport, then you will have more ice reaching this part in the Atlantic. Then this is Greenland, by the way, and this is Canada. So this is the Labrador Sea. You will have much more convection when you have less fresh water. As when you have more fresh water, you will tend to have more lighter water on top, and then you will have more stable ocean. So you will have a reduced convection when you have more freshwater transport crossing the Fram Strait. And this is also a bit of well, this is really important to understand how we do and how what's the uncertainty that we produce just by changing the resolution. Because when we do climate simulations for the future, climate projections, we can see that we do expect an increase of fresh water in the future across the Fram Strait, and we have a decrease in ice transport. So there is some uncertainty, but in general, it is expected that with warming in the Arctic, we will have much less ice going towards the Atlantic, but it will be compensated by an increase in freshwater transport. So as a summary, we have that coupled GCMs have a dependency towards model resolution, showing lower ice volume over the entire Arctic, higher freshwater volume over the Beaufort Sea, and lower freshwater volume over the Laptev and East Siberian Seas, lower ice transport and at higher freshwater transport across the Fram Strait, and lower convection at the Labrador Sea. Thank you.
Questions? So you showed us how model resolution makes things better, but where would you put the increase in resolution if you could choose? Atmosphere, ocean, what's?
Oh, okay. So what I see is that there is a super big impact in the ice. There are some models that are really much more sensitive to resolution. I think, unfortunately, it's really needed to tune the model again once you change the resolution to have a better representation of what you have. But there is, just by changing the resolution, you have a big change in the system already, unfortunately.
Question?
I have another one. You see a reduction of the sea ice with higher resolution. Can you speculate why that is?
Well, I think, the parametrization would be one thing, how the model is parameterized. But there is also probably some papers saying that there is more transport of heat towards the north at high resolution. So yeah, maybe.
Being more in the atmosphere, I think this is really, really interesting, and spend a lot of time up in the Arctic and see how the ice fields are changing. It's really interesting, but how exciting, I would say, to get a better understanding, but how much data, actual observations, do you have, and what do you need?
Yeah, well, we use only the reanalysis. The reanalysis are 25, Orca 25, so it's high resolution, but unfortunately the observations, I mean, in the late, we lack of longer time series. That's, I mean, you can have maybe, for example, yeah, I mean, you can have an idea of how this, the circulation works and the internal variability with the reanalysis, but I mean, the time series are quite short. So,
how much do you use this kind of seabed observation sites like Hausgarten?
Well,
do you need more of those?
I think, well, I think maybe it would be interesting to include some observation besides the reanalysis that I'm doing, but the reanalysis, they use the observations, yeah. I haven't used them personally, but maybe I should, yeah.
So in the start you were talking about that the freshwater transport is partly by sea ice and partly by less salt water.
Yeah.
So did the total Arctic salt content change when you changed the resolution?
Sorry?
The total Arctic salt content, did that change with changing resolution?
Well, you initialize your model and then they start from the same state, but how it changes, I mean, it develops differently once you already change the resolution. It shouldn't start with different ice volume from scratch.
No, I understand that, but I mean, so the total salinity content in some sort of Arctic domain that you can maybe use, did that change because you have an ice reduction in the low resolution and maybe there's more ice export out, and does the melted water stay there, or does it go out? Does the total amount of kilos salt in the Arctic change after a while?
Yeah, in some models we saw that actually it was really the atmosphere playing a big role on reducing the ice, and then there was no ice formation, and the ice contributes a lot to the fresh water. And it was a really complicated feedback. I mean, just by having warmer the Arctic, you would have much less ice, and then afterwards, maybe if you have a really long simulation, you will have an impact on how much fresh water you have.
Yeah. But this was not studied in a control simulation, but in a present-day simulation.
Also, well, pre-industrial, also some pre-industrial simulation, yeah. But they are not so long, unfortunately, those that I'm analyzing.
I'll talk to you later.
Yeah.
Hello everyone, my name is Luisa, I'm from MISO, and I'm, do I have to? Okay. Okay, so if we look at clouds in the Arctic, they are very important for the total energy balance we have in the Arctic, so they have a large influence on the latent and sensible heat, and also on the temperature that we have on the sea surface, so they also have quite an influence on the melting of sea ice, for example. There are a lot of complicated processes going on in these clouds. So we have the radiative cooling on the top of the cloud, and that induces some kind of turbulence inside the cloud. And also, yeah, we can also have like precipitation, so the cloud can stay a while, or then it precipitates, then maybe it's gone. And all these, like all the radiative properties of the clouds, and also all this kind of quite complex microphysical process, they depend on the phase of the cloud. So they depend on how many water droplets we have in the cloud and how many ice crystals we have inside this cloud. So depending on this kind of ratio between these two phases, the cloud can survive quite long, or it can also like vanish quite quickly. For example, if the cloud changes the phase from the water phase to the ice phase and then only consists of ice crystals, they can precipitate quite fast, and then the cloud is just gone. So what we look at in our study is how actually does a cloud droplet in a water phase becomes an ice crystal. So looking at that, if you have a cloud droplet inside a cloud, normally it doesn't freeze so easily, so you need quite cold temperatures for a cloud droplet to freeze. But in the mixed phase clouds that we look at, these temperatures are normally not cold enough. So you need something else which triggers the phase transition of the cloud droplets to ice crystals, and that are where the aerosols come into place. So if you have an aerosol particle inside a cloud droplet, then it can already freeze at warmer temperatures than the cloud droplet alone. And the temperature that these cloud droplets then start to freeze, that depends on what kind of aerosol particle we have inside our cloud droplet. So there are different aerosol particles which can trigger this phase transition of the cloud droplets. There can be mineral dust, or it can be pollen, volcanic ash particles, soot, or some kind of bacteria or organic material. So if we think about the Arctic now, there are not so many particles actually, because we don't have a mega city inside the Arctic, or we don't have a desert just next to it. So what kind of aerosols do we actually have there? So there are two different sources we can think of how we get aerosol particles into the Arctic. So that's either aerosol particles which come like from far away, so from, for example, from Asia, from the Gobi Desert or some other areas, and then they get transported into the Arctic coming from above the boundary layer and get mixed into the cloud. Or what we can also have is sea spray, so we can have some aerosol particles like marine gels or some kind of organic mass which comes up from the ocean into the cloud. So that's the source up there. So what we are interested in our research topic is how sensitive is the lifetime of the cloud on the different aerosol species that we have, and how sensitive is it to the vertical aerosol profile. So if we think about these two sources, we have like two components. We have either the aerosols coming from above, or we have the aerosols coming from below. So they enter the cloud at different heights, but we also have a different chemical composition depending on the aerosol type we look at. So if it's a transported aerosol, it might be more likely a dust particle, and if it's a local aerosol, it's a marine type of thing. It's very likely not a dust particle or something like that. So how do we try to answer that question? So first, we did try to think of some good vertical aerosol profiles. So we estimated some profiles for the local sources and some profiles for the transported aerosol sources. Then we also have to describe the freezing of these aerosols. So as I said before, the freezing of cloud droplet inside a cloud depends on what kind of aerosol we have. So if we have a dust particle, that freezes much easier than a marine aerosol, for example. And then the last point is, so we take both together and then we do some large eddy simulation modeling with Mimica, and we simulate one Arctic case study and see what we get out of it. So here you can see the 4 different profiles that we used in our study. So the blue one is the one for the transported aerosols. So you can see that we have quite a high aerosol concentration from like in the upper layers. So the height is on the y-axis, and then we don't have any aerosols anymore, like below a certain height. That was used from measurements which were done at the ASCOS campaign in the Arctic quite some time ago. So they did some helicopter profiles of aerosols. And then for the local aerosols, we did some regional modeling using the model CosmoArt and derived this kind of light blue profile that you can see. So we have quite some aerosols coming from the surface, but then the higher you go up, the less aerosols you have because they're coming from the surface. So there's not so much going on above 1 kilometer. And then just to have some kind of reference, we also use 2 constant profiles, that is the red and the purple line, which is just straight, so we just assume a rather low or rather high aerosol concentration. And just a few words about the model that we are using. As I said, we use the large eddy simulation model Mimica, and we simulate one Arctic case also from the ASCOS campaign. That was in August 2008. we use a rather, so it's not like a weather model, we use rather a small domain size, and the resolution is quite high, so we have a time step of 2 seconds. And yeah, we simulate just this one cloud case, so the simulation time is 12 hours. And then the size distributions for the aerosols we also take from the ASCOS field campaign. Yeah, that's basically it. So here you can see how the reference case look like. So maybe we first look to the right, so you can see on the upper plot on the right, you can see the water inside the cloud, and on the lower plot on the right-hand side, you can see the ice. So what you can see is that it looks quite similar as in the sketch I had before. So we have the liquid phase on top of the cloud, and then we have some ice particles below the cloud droplets, and they also fall out, which you can see by this kind of streams that go down. It's a bit not so easy to look at these plots. That's why we look at the kind of easier version on the left. So on the upper plot is the liquid water path. So that's kind of all the water inside the cloud kind of summed up. And the lower one is the ice water path. So that's all the ice summed up. So, and the black line shows how the standard of how the cloud looks like in the standard case in our simulation. And the orange lines is the observations. So now we will just look at the results for the different simulations, and we will first look at the different aerosol species. So how important is it if we have dust compared to a marine aerosol? And again, it will always be the same plot, so the liquid on the top and the ice on the below that. And we will always compare the simulation results to the black line. So that was our standard case. Now we also added a gray line, which you can see up there, and unfortunately here in the, I don't know, somewhere here. It's okay. So that is a simulation where we don't have any ice, so we just switch off all the ice processes, so the cloud has to stay liquid. That's why the liquid water path is quite high, and then the ice water path is at 0, so it's not such a problem that you don't see it. Now we add the results for the simulation where we assumed that all the aerosol particles are marine aerosols, and you can see we get more or less the same as in the no ice case, so the marine aerosols don't form any ice in that case. Now when we add the results for the dust, we did like 3 different simulations for the dust aerosols, assuming different percentage of aerosol is dust, so either only 1% of all the aerosol particles we have is dust, or 5% or 10%. And you can see the 3 different purple lines. So if we assume only 1% of the aerosols is dust, we get quite a similar liquid water path and also ice water path to the standard. And if we assume it's more aerosol particles is dust, then we see that the liquid goes down quite dramatically, and also the ice goes up quite a bit. So summarizing this, we can say that the liquid and the ice we have in the cloud is quite sensitive to the assumptions which aerosol type we have. And if we use a rather inefficient aerosol type for the freezing, like the marine organics, then we don't get any ice in the cloud. So we don't get a mixed phase cloud. We just stay with a liquid cloud. So that is now the results assuming one of the cases before. So we assume now that 2% of our aerosols are dust. And we look at the different vertical profiles, so the 4 profiles that I showed you before. And you can see that most of the results are actually quite similar. There's only one simulation which is very different. That is the purple one, where the liquid water path is basically 0. And you can see here, when you look at the ice water path, that we have very, very much ice in the beginning, and then the cloud is just gone. So it seems that the liquid and the ice we have inside the cloud is less sensitive to the vertical profile, but if we assume too much aerosols, like this very high constant profile that was the purple line, then we lose the cloud very quickly. And with that, I'm coming to my conclusion. So to answer the question, how important are the marine aerosols to the Arctic mixed phase clouds, we could see that if you look at the freezing ability, that if we have a an aerosol which triggers the freezing very easily, or a very high concentration of aerosols, then we get the ice formation we want to have. So we get some ice inside the cloud, but if it's too much, then we lose the cloud quite quickly. When we look at the aerosol profiles, it seems that the marine aerosols reach high enough up to trigger some ice inside the cloud, but the vertical profile is a lot less important than the chemical composition of the aerosols. And with that, I thank you for your attention.
Thanks a lot. Other questions?
Are you doing something to maintain the temperature of the cloud, or is the radiative cooling just allowing it to just cool down steadily throughout the simulation? And I was particularly wondering, in the case where you don't form ice, it seems like eventually it would just get, because of the radiative cooling off the cloud top, it would eventually get cold enough that you would just get homogeneous nucleation. I was wondering when that would occur.
That would be a long way to go within 12 hours, because the cloud is quite warm at the beginning, but the temperature evolves throughout the simulation time. So.
But I mean, how much does the temperature of the cloud decrease over the 12 hours of the simulation?
A few degrees, I guess,
okay.
But not like, I mean, we start at -5 or something, so to form homogeneously cloud droplets, we would need -40, so. Yeah. It's very unlikely that we get there.
Yeah.
We have time for one more question.
If we should simplify it very much, you have the Arctic haze in the spring, and during the summer you have the internally grown nucleation type particles. They differ quite a lot in size and composition. Well, it's about the same number concentration. How could you see differences in cloud for these two types? What differences would you?
Yes, I mean, there are two different aspects to look at. So I'd only talked about the freezing part now, but of course there's also cloud activation first, so you need the water droplets first. So we also looked at how much the hygroscopicity influences the, if the cloud forms at all and how it looks like. And but I would say the size is more important than hygroscopicity, actually, from what we see for the case we looked at.
Okay, thanks again. And then let's move on to the next speaker, which is Velibor Zeli.
We're also contributing to this large project. And I'll be talking a bit more specific just about how we can implement some new ways of treating turbulence in our climate models. So what we usually consider as turbulence is the transport of momentum by turbulence or transport of heat by turbulence. And this is a key effect in the atmosphere, so the key transport in the atmosphere. So if we would be able to solve these equations without parametrizing modeling, we would actually have the really accurate value for these transports. However, this is not possible, so we do some tingling here, and if we would solve after this tingling, if we would solve these derivatives here, we would be able to solve these equations. We would still get some modeled versions, but this would be very, very accurate. So this would be Mallory-Yamada level 4 closure. However, if we would just solve K-theory, and if we would use K-theory for turbulence modeling, which is very well known and spread, then we would just use some very simple simplifications for turbulence. However, what we want to show is that we can attain this level of physics in the turbulence model. So we could contain all of the physics from these equations 1 and 2, and still express these equations, but without these derivatives here, and then we would have explicit relations which would solve, which would be able to solve much more numerically cheaper, and these would look something like this. Instead of the derivatives, we would just express the terms as a function of some gradients and turbulent kinetic energy, potential, turbulent potential energy, and so on. So I want to show you, so now after implementation, we ran some cases, and I want to show you what are the contributions and what are the importances of treating this turbulence with more care than just by K-theory, for example. So if we would run the golden diurnal cycle, so basically what we do is we take our model, and inside of the model we force the model with these boundary conditions for temperature. So we're forcing the model to be stably stratified, atmosphere to be stably stratified in this region when we're setting the temperature at the surface in this way. And then later we're setting the temperature of the surface to be in this way, and so on. We're actually having night and daytime, and again night and daytime, and so on. So this is what we're doing. And this was first done in Gunilla Svensson et al. 2012 paper. So we would actually get parts of the day in our model when we have unstably stratified atmospheric boundary layer and stably stratified atmospheric boundary layer. And now we want to see what's happening in these boundary layers and how we can what we can capture. So if we run our model with this setup, then if we look at the turbulent kinetic energy, we actually see that during the nighttime it's very low. Turbulent kinetic energy is located very low in the atmospheric boundary layer. But during the convective part of the day, then it's transported all the way up in the atmosphere. So we're having quite a lot of convection in this region here. But if we look now, what is very interesting, this is the log contour of Z over time, right? So if we would look at these regions here, so this is the upper part of the atmospheric boundary layer, where the atmospheric boundary layer is actually stable. But there retains some amount of turbulent kinetic energy here. So this is very interesting, since this is the leftover from the previous day. And then when we're coming to the next day, we're able to build up on this amount from the previous day. So if this model, turbulence model, would be a simple K-theory model, then there would be a cutoff right about here. So there would be no decaying turbulence that is left over from the previous day. So this is something that most of the climate models nowadays have, that they just have a cutoff line here. But with more physics, with more physical representation of turbulence, you could actually get this region here. So another thing that the model is very capable of doing is distinguishing stable and unstable turbulence. So it's able to, for example, during the stable atmospheric boundary layers, like during the nighttime, we would actually expect that everything, all the fluxes of momentum and heat transport are transported in the horizontal direction. So we would have pancake structures in the atmospheric boundary layer. And during the daytime, when we have convection, then we would have transport in the vertical direction. So this is typical. And now if we would, so this would, if we look at the variances, this would look for stable variances. These two would be larger than the vertical ones. So the horizontal are larger than the vertical. We're damping. And if we're in the unstable regime, then the vertical ones are larger than the horizontal ones. So the model actually can capture this kind of behavior here. And we see that the vertical variances are smaller than the horizontal variances for the stable part of the day. And this corresponds to this part of the day here when we're actually in the stable regime. And for the unstable part of the day, we see that the vertical variances, here this line, would be larger than the horizontal ones, since we're having the development of turbulence in the vertical direction. Except at the wall, where it's very physical. We're expecting to come close to the wall, and then we're damping the vertical fluctuation. Since we're close to the wall, there is no transport in the vertical direction. So with simple models, there would be just one line here in both cases, because simple models are isotropic, so they don't see these anisotropy effects. So we would just have this way of behavior. So we would spread momentum and heat in all directions equally. So now I want to show you a bit more qualitative analysis that we did. We compared our results to the LES from the paper from Sullivan et al. 2016, and we're modeling the stable boundary layer. And again, we're doing this by prescribing the temperature at the surface. We're having homogeneous terrain, and we're just specifying the turbulence cooling at the surface with 4 different simulations, 4 different cooling rates. So 4 simulations with different cooling rates. And these cooling rates are 0.25, 0.30, 75, 0.5, and 1 Kelvin per hour. So we're cooling the surface quite fast, and we're expecting to build the stable boundary layer. Okay, so if we look at the results now, we see that our model results for the horizontal wind speeds with height, and the LES data. This is a very high resolution LES, very accurate. So we see that we have all the structures that already exist in the LES. So if you look, for example, the yellow curve corresponds to the cooling rate of the highest cooling rate, so the most stable atmospheric boundary layer. So you would see that actually you see this part here, which is also captured by the LES. So there's a high similarity between these two. The only difference that we see is in the height of the planetary boundary layer, but I have an idea of why that is. And this is for the temperature profile. So the temperature profile for different cooling rates has again very high similarity with the LES, and we again see these structures here from the low-level jet. And then this is a very nice thing that we have in our model. So without any additional cost, we can have horizontal fluxes. So if we have a stable boundary layer, then the horizontal fluxes are very important. They're much more important than the vertical fluxes, right? Since we're spreading everything in the horizontal direction. And the simple models would fail here. They would fail tremendously. So they would just give zeros, whereas our model is able to capture this kind of behavior on some level. So we're actually capturing the change. So this here is the in the streamwise direction heat flux, and this here is the span-wise direction heat flux. So we're actually getting the change of sign correctly, so that's one thing. And in the above layer of the atmospheric boundary layer, we're capturing quite well, whereas very close to the surface, we're not so sure how LES can resolve this part very close to the surface. So we're not sure what's happening here, who is right here. I mean, it's very questionable. So, but in the above layer, it actually looks quite well. So the takeaway message is that by improving the atmospheric boundary layer turbulence parametrization, you could actually have some processes that are very important in the atmosphere and important for Arctic studies, like the residual turbulence or like these horizontal fluxes, which are completely not captured. And it's an explicit model, since that means that it's fast. It doesn't solve the prognostic equations. And one more thing is that this model produces grid-independent results. So it doesn't matter how you change your resolution, it will produce very stable results, with which I see many of you are changing resolutions, checking out everything. So you would not have any problems with changing the resolution here. You would know that turbulence is always the same. So, thanks.
Thank you. Questions?
Very interesting. Basically, the question is always, you do that simulations now for Arctic kind of climates. Would it be at some day possible to have one turbulence model which applies to all climate zones like tropics and Arctic, or do you think that you need some modifications depending on which climate you are in?
Well, the physics of turbulence is captured in those first equations that I've shown in the first slides. So the physics of turbulence should not change. Only the terms could be changed. For example, if the atmosphere is more neutral, more stable, or if there is less shear, more shear, if it's buoyancy driven or shear driven. So I don't think that this model would have any problems to work in any region, but it's very well suited for the stable boundary layers, since you have these horizontal fluxes which are more dominating than the vertical ones in the stable boundary conditions. So we're solving the wrong things actually in the stable boundary conditions. We're solving the vertical ones instead.
Yeah, actually, I have two questions about water vapor. One relates to the previous question. So one difference if you're applying it in the tropics is that there's enough water vapor that the buoyancy due to water vapor comes in and affects the stratification. I was wondering to what extent that could be incorporated, but also getting back to the Arctic, is latent heat release in the boundary layer something that you can incorporate, or is there some reason that that's not an important effect in modifying the turbulence?
That's a very good question, yeah. So latent heat is very important, and so far we didn't couple it because this mathematical tool that we're using actually to go from prognostic equations to explicit relations is very sophisticated. So it's very hard to relate these two, and if we would actually, heat is an active scalar since it's going to change the temperature, and then temperature is going to change the wind field, then we would have actually a very hard time to couple them. But that's something that we're looking into and that we would really like to see, since it's very physical and so far very well behaved. Thank you for your question.
Hello everyone. So my name is Marianne and I'm a PhD student here at the Physical Geography department. And here I will present studies that I've been doing with the Zoology department. So we are moving on to more study of species interaction in the mountain tundra, and specifically on tundra predator guild. So my title is The Fluctuating World of a Tundra Predator Guild, Bottom-Up Constraint Can Overrule Top-Down Species Interaction in Winter. So here I will give a talk to show the importance to focus also on the winter perspective when studying species interaction in the mountain tundra. So with global warming, well, global warming is expected to affect ecosystem structure and functioning, and this is especially true over northern latitudes, where climate and resources should impose relatively strong constraint over the system. So when it comes to the main body of theory on how biodiversity is shaped over a northern ecosystem, it suggests that the relative importance between bottom-up constraint or top-down effects would vary over latitude. So the higher you go in latitude, the more unproductive the tundra would be, and then the more herbivory biomass is limited by bottom-up constraint. While if you go more down in latitude, then top-down effects would increase with predation pressure and competition increasing, and then limiting more the different level of the trophic levels. So This suggests that with warmer temperature, there would be a switch from a more bottom-up control to a more top-down regulated system. And this is likely to be strengthened with the expansion of boreal species northwards. So here it is illustrated with the red fox coming northward onto mountain tundra and having a strong negative effect on tundra, native tundra species, and in this case the Arctic fox. So here is the main starting message. With global warming, top-down effects, so predation and competition would become more of a significant structuring force over the mountain tundra. And this has been already observed quite a lot in summer, but now I will come on to the fact that Arctic ecosystem is a very highly dynamic ecosystem, meaning that this strong resource constraint would also vary in time. And in that sense, seasonality should not be overlooked when studying species interaction. We should also think of the winter perspective. And most of the studies here, when studying species interaction, are mostly focusing on summer observation, because that's when we can actually do the fieldwork. And not only there is variation in constraint between seasons, but also we should think of a main characteristic in the system, which is here the rodent cycle. So with a different phase of the rodent cycle, all level of the food web is affected, where the predators would track the abundance of the rodents, and this has an effect in terms of competition and also predation pressure over other species than the rodents. So in that case, also every year is different with different resource abundances. And this can also have an important effect when we are thinking of the dominance ratio between this bottom-up constraint dominance or more top-down effect regulation. So here my main point of focus was to study the structuring rules over this mountain tundra community. Would these top-down interactions that are meant to increase with global warming and have been already observed in summer, would they still prevail in over the bottom-up effects in winter, and also when the rodent abundance would be lower, when the resources are low? So the main point for focus here started with the interaction between red fox and Arctic fox, knowing that in summer it has been observed that red fox would suppress Arctic fox and be an important threat to its persistence. So here there is a strong interference competition going on between these two species. But I was interested to look at the mountain tundra community in winter. So here in this case, looking also at other predators that could affect the potential presence of red fox and also Arctic fox. And in this area that I will present in the next slide, the other large predator that was detected was the wolverine. And no wolf or lynx were in this area detected. And wolverine as a potential top predator was predicted to potentially suppress Arctic fox and red fox. And since I was testing whether top-down effect would prevail over bottom-up effects, then these predators, their presence were tested to suppress prey presence, prey abundance. And in this case, in winter, ptarmigan is important. And here you don't see the rodent, and this is because in winter it's very difficult to detect it since it is under the snow. So the rodent abundance was taken as a treatment, and every year analyzed, was classified according to the phase of the rodent cycle and whether there was a peak in the summer before that winter. And then came also the main bottom-up factors. So in this case, I'm just presenting a selection so that the final ones that were in this model, so the altitude, which would relate more to harsh climatic condition and difficult terrain, and the aspect of the mountain, which would relate in this case to more the snow accumulation. So I could not show this in this presentation to make it short, but more or less the mountains in this area were oriented either southwest and more northeast. And on the more southwest face of the mountain, there would be less snow accumulation due to stronger solar irradiance, and also the predominant wind would drift the snow over the northeast side of the mountain. So, but I will come back to this in the results. And then the primary productivity was also taken in account in this model. And just to talk quickly about the methods. So the species were detected and surveyed through snow tracking using the wildlife triangle scheme, which is a protocol that has been established already in the 90s, but more in another kind of habitat in boreal forest. So here, this protocol consists of triangle in the shape of triangle of 12 kilometers long, and these were done every year over the open treeless tundra in Vindelfjällen Nature Reserve. So one of the remaining areas where Arctic fox is present in Sweden. And just to show quickly some of the results, because I couldn't present all this in 10 minutes. So here I'm presenting a low winter, so where the food resources should be low since it's after a crash of rodent in summer. And what you can see to start with, so this is a structural equation modeling where I was testing the species interaction. So first, there is no top-down effect observed in this model, and what you can see is that the red fox and the ptarmigan is more constrained bottom-up from the westness, so the side of the mountain where there would be less snow accumulation. And also there was a surprising positive relationship between Arctic fox and red fox, which in this case would suggest that when the winter conditions are quite harsh and when there are low food resources, then instead of having competition, the environmental constraint would be more influential and make appear that the species could appear in the same areas. And then, if you look now at the phase of the rodent cycle where the food resources would be low, so this would be a winter after a peak, would be high, sorry. So in this case, we can see that there is still a bottom-up effect on the red fox coming from westness, but also coming from ptarmigan. So here the arrow was going down because that's what I was testing. I was testing a negative effect from red fox onto ptarmigan, but instead it was a positive relationship. So the arrow should be actually up, and it's a bottom-up effect going on. And you can see that there is a top-down effect coming from Arctic fox to ptarmigan, but this is happening at the same time that there is also an altitudinal segregation between altitude and Arctic fox and red fox, suggesting that here there might be actually red fox monopolizing the most productive area where there is like less snow accumulation and more prey, while the Arctic fox would be more confined in the higher range of the altitude of the mountain. So can bottom-up constraint overrule top-down interaction in winter? Well, in this model, the top-down effects were weak and fewer than expected. And yes, the bottom-up effect appeared dominant in this season. And this was particularly clear with the red fox, which is at the edge of its distribution in the mountain tundra, the difference of its typical habitat. And it is true that red fox was more limited bottom-up rather than exerting a top-down effect. And also here I didn't present it, but there are also analysis of spatial patterns that we've been doing in this study, and showing that the cold specialists, so Arctic fox and wolverine, had much more of a variable pattern over space and time, suggesting that they were more like as cold adapted, so they would be more adapted also to the unpredictability of resources in winter, which would also explain why there would be such a lack of competition between predators in this season. And the main take-home message is that so when there are winter conditions and the food resources are low, then there is this dominant bottom-up control. And this shows that the importance of seasonality and also pulse resources that would have an important influence on the dominance ratio between bottom-up and top-down regulation over the system. And it also shows that this interaction between summer and winter is important to take in account and to be able to determine the changing rate of the northern ecosystem. So in this sense, it's also, this study shows the importance of studying species interactions through the scope of seasonality, and that the winter's perspective should be more taken in account in community ecology, especially to be able to grasp the effect of global warming on mountain tundra. Thank you. Yeah. Thank you for letting me present here, and I would like also to thank the CORSAR and Bolin Center who funded this study, among others. Yeah.
Thank you. Do we have questions, Marianne? Sure.
If someone were to hand you a climate simulation for the Arctic in, say, 2030, how would you use that to, with your species interaction model, to say what happens to this particular tundra community? Is that possible? And also, what would be most important for the climate modelers to get right in order to enable you to project how things change?
In terms of constraints, it would be definitely the snow. The snow would be very important to look at, to be able to understand actually how resources are partitioned over the landscape. And this is really missing here. So we'll use topographic features to be able to have an idea where actually the snow is hardest to move in as a landscape. And this is definitely something that we would be lacking. So precipitation of snow in winter. And also icing events, I mean, this is also studied with other species, but it can affect, for instance, the lemming very much. And so, yeah, definitely there are, I would say, that's the main two elements. But this would be very important to link it with studying the species interaction.
But is the species interaction model of a nature that it can take those climate inputs directly and then turn that into a prediction, or does something else have to be written in as an intermediary to actually close that gap?
I guess it's the stronger the climatic constraint, the less top-down effects we would see. So that's the main baseline I would have here. And the more bottom-up constraint would be the system. So that's what I would suggest. Yeah.
So it looked to me, when you had your correlations there, it looked like the altitude had like the strongest correlations overall with everything. So is that related again to snow, that altitude determines how much snow you have, or does altitude determine how much food you have, or why is altitude the main thing? And what?
It's definitely that it's harsher constraints with higher altitudes, but I didn't specifically assume that there would be like more snow, but it would be definitely harder to like persist there. That's for sure. Did I answer your question?
Yeah. Yeah, so let's thank Marianne again.
So we go back to the Arctic Ocean a bit more. But it's been fun listening to all these talks and see the implications and how these things interact here. And I'd like to thank the organizers and for arranging the schedule so that I can actually get in here on a day when I can't possibly do it tomorrow. But so we want to use constraining Arctic methane source strengths with ambient measurements. Now, what we're doing now is there's very little science in this talk, but rather this is more of an advertisement and perhaps a rationale and perhaps a wee bit of a plea to keep these kinds of measurements going and the rationale for them. There's three broad objectives for this program description that I'm giving you that has these different aspects. First, this high-quality survey of ambient methane in the marine boundary layer of the Arctic Ocean. Now, high quality, what do I mean by high quality in the first place? It's just simply that we understand the precision and the accuracy of the measurement that we're actually making. What is it, how well do we know that number ultimately? Why methane? Methane's kind of, I look at it as kind of the dead canary because of the coal mine. Essentially, the idea that methane, even though it's only 2 parts per million or 2,000 parts per billion in our marine atmosphere, or is that I mean that's 2 parts per million in a 21% oxygen atmosphere. That's pretty wacky. To my mind, that is an indication of waste, of somehow the ecosystem is not efficient. And something like methane now acts as, because of its it's got a very strong biological, geological, as well as a chemical dynamic. So it's a particularly interesting, sensitive, perhaps indicator species of changes. And so we need to perhaps use some of these mass measurements in order to understand something about our climate, our climate scenarios. And then we get a sense of what's there, and we want to know how fast that might be changing, right? So we want to understand something about and better parameterize these air-sea exchange rates. And then finally, we need to integrate these data into better parameterizations of those notions of exchange so that we can understand the sensitivity of the methane concentration dynamics in our atmospheres. So and when I'm talking about model parameterizations here, I'm talking about at all scales, right? So there's a number of different approaches here, and some of which we've taken across very large differences in scale, both temporal and spatial. Oh, this is a really complicated, messy slide, but just the idea to give you the notion of an operational setup. And so the Arctic Ocean's kind of remote, kind of hard to get any sort of permanent measurements there. So we have to use ships of opportunity, and one of the finest ice-breaking ships I've ever been on, of course, is the Odin. And so with a number of friends here, we've managed to, this is essentially just give you a notion of what the profiles, so we're making measurements close to the surface. So we're at the surface boundary layer, well within it. Now, we're also working with the physical boundary layer meteorologists in order to understand something about the eddy correlation of that of those fluxes. Now, that correlation comes out of the covariance, and to understand that variance, we have to be able to make those measurements to a known precision, right? So that's all what we're doing here. And then there's also a very important component in that, and that's in the surface water concentrations, because there's a number of common models that we use that rely on these gradients. And so the efforts of the VGAS system here of Mark Geibel and our friends over in ACES, that we can start to understand something about that precision. Now, what kind of information do we get out of that? Again, using ships of opportunity, and with the Odin, and over the past five or so years, we've managed to keep our equipment aboard this ship and make precise measurements along these various paths there. Now, one thing back here is that I wanted to point out in this are these notion of these target gases. How do we use those target gases, and how do we assure our accuracy of measurements? And that's an opportunity for us to now tie our observations into internationally recognized standards and standardization, so that this notion, when we say something is 1 microatmosphere in the per atmosphere, that we have a good handle on what that number is. And so this is the kind of distributions we're getting. Now, that doesn't seem all that exciting. You know, it looks like it's varying about 100 parts per billion all across the Arctic Ocean. The colors here only represent times of year, right? And these are all summer measurements, essentially. So that's when the ship is operational in the ice. So when we can take advantage of those measurements. And the profile measurements tell us a couple of things here that we can now, you know, we're precise enough, we're good enough that we can see the secular increase in methane. This lines up very well with observations at something like Alert or Barrow or some component of the NOAA FLAS network around the. And the other thing is when we lower when we're anchored and have the opportunity downwind somewhere in more shallow water, that we actually have increases, which suggests there's also a source at that water surface. But this is a really subtle source, and then so that means that our models and our parameterizations have to be really, really precise. Okay. Oh, I just said all this stuff here. Here's that increase. So over the past, the time of these measurements here, we're looking at about 11 parts per billion per year increase in the monthly averages that are measured in ALERT, which is the furthest north station of the NOAA system run by the Canadians. And this is that increase. And it also gives you a sense of what the importance of the Arctic is in these kind of observations. Now, we've heard very much about that heat transport and Arctic amplification, all these kinds of things. And then what are the implications of these increases? And so that's up to many of these folks, you know, like that. And so understanding that and then understanding that feedback becomes important. Let me check my important notes here to make sure I didn't miss something. Excuse me. Right, did that. The cross tension, all right. And the other thing is to notice these objectives now that I had delineated in that very first slide, or second slide rather, are, you know, they spill over to each other. And that spillage is kind of has interesting implications. Now when we look at, you know, not only just that secular increase, but, you know, spatially, it gets kind of fascinating, you know, because it's not, you know, the methane is not the same everywhere. And we can then take those data that we collect here in the ambient, in that surface ambient layer, and then compare that to a standard model that using the surface water concentrations and the turbulent forcing of those gases, we can make flux calculations. But at the same time, we can see what these distributions are very different. Here's a cruise alongside of Svalbard and in the Central Ocean. And, you know, perhaps there are things that are showing up as when we get into areas with very thick ice versus disintegrating ice versus open water, we get very distinct differences in the numbers. Now, so we talked about this, and that gave you a sense of the ambient methane in the marine boundary layer, but we're also interested in those fluxes. And again, using like those kind of gradient-driven turbulent or gradient turbulent-driven fluxes, now we can make these calculations of what those exchanges might have to be. And again, we see, you know, very strong variations. This is from the 2014 Squirrel C3 cruise, and we see differences in those fluxes, you know, in the local fluxes. Now, all right, that's one potential model. And then another potential model that we use because of that setup and with our operational setup and with the help of our physical boundary layer friends in, at MISU, you know, we can now try to make measurements of a direct measurement of those fluxes using the surface turbulence structure and the concentration variability. Okay, eddy correlation, right? And so now we can move from, you know, even local scales at high frequency, and we see various differences in the distribution of these fluxes. Now this little hot flux right here is when we're closing in on one of these subseeps. So that's pretty fascinating. Okay, now we can see something about the distribution and what might be changing. And an important, now let's go to the biggest scale, right? We can take those ambient data and then we can force them into some of these like chemical transport models and get a sense of what that flux is to try to constrain this whole aerial flux, besides all those, adding up all those little individual ones. And we get numbers like this, okay? So our gradient-driven numbers about 3, the eddy covariance about 1.5, these are consistent. Our inverse model calculation now is has the largest range. Can we improve that number? Can we improve those modeling? You know, like I'm a measurement guy, so I break models for a living, right? We don't learn anything until the model doesn't work, right? So here, and also now we can also extend that other aspect because another portion of our measurement program is using these new laser technologies that allow us to make very highly precise isotopic measurements. And so we moved those instruments that we initially had put on the ship, which also I challenged my French friends to use in their simulations. We've moved it up here onto New Olison. We've got differences in all these different sources. Can we learn something about specific sources? Can we learn something about the dynamics of those sources? All right, that was my advertisement. And of course, this is a huge, so many folks have, my luck has held out with all these smart folks who've taught me cool things. So it's really so much fun, and with some of the help of the folks on the Odin and Norse Polar for the new Olison installation, and the cash to keep people working. But yeah, thank you.
Thank you. So unless someone has a really quick question for Patrick, I think we'll just say thank you to all the speakers, and it's lunchtime, and we'll come back at 1:30 for extreme events, right? And yeah, thank you all for listening.